As our next step in our review of the mathematical underpinnings for the course, we'll look very briefly at graphs. I'm not going to spend a whole lot of time on this, even though we are going to use graphs extensively in this course. This is because the main thing that we're going to use them for is a graphical representation of the machines that we're working with, and what we'll discover almost immediately is that this depiction is very intuitive and very easy to work with. But there are going to be some problems that we will visit over the course of the semester that will draw on some deeper aspects of graph theory, and so we want to be familiar with some of the terminology and some of the concepts. A graph consists of vertices and edges. The vertices, also referred to as nodes, generally represent a thing, a noun of some kind. We usually put labels on nodes, if nothing else, just so that we can refer to them. Edges are lines that connect one node to another. Graphs are a means to represent relationships, and the presence of an edge represents that some kind of relationship exists between the two nodes that it connects. We can also put labels on edges when we need to provide more information about the nature of the relationship beyond its mere existence. Graphs may be either undirected or directed. An undirected graph just says that the relationship being depicted exists between connected nodes, whereas a directed graph says that the relationship depends on which node we are coming from. An example where an undirected graph might make sense is on a map showing distances between cities that are connected by interstate highways. Since highways are almost always bidirectional, the distance going in one direction is going to be essentially the same as when going the other. But a map depicting the city served by a particular airline might be more complicated. The routes in one direction might be quite different than in the other direction due to aircraft separation strategies or the influence of prevailing winds at different flight altitudes. It's also possible that the airline might only offer service in one direction between a particular pair of cities. For instance, it might fly a circular route amongst several cities. We would represent these relationships using a directed graph. Now we can talk about how to formally define a graph, and we'll use a combination of sequences and sets. Since a graph consists of two things, nodes and edges, and since these two things are not interchangeable, we describe a graph using a two-element sequence, or a two-tuple. The first item describes the nodes, while the second describes the edges. The nodes themselves can be described by a simple set that contains the label of each node, yet another reason to label the nodes. The edges are also a set. Each member of this set is a tuple that describes one edge. If the edges are unlabeled, then an ordered pair will suffice, and the first term is the node that the edge starts from, and the second is the node it goes to. If the graph is undirected, it is understood that the edges are bidirectional. In the case of an undirected graph that is also unlabeled, we could actually use a set instead of a tuple to describe an edge. But even with an undirected graph, as soon as we add a label, we need a tuple. So we generally just use tuples to describe edges. If the edge is labeled, that becomes the third item in the sequence. So let's take a look at an example of a formal definition and the graphical representation of that same graph. Our graph has 5 nodes, the labels of which are listed in the set V. The edges of this graph are directed and labeled, so each element in E is a 3-tuple. There are 10 elements, so there are 10 edges. You should confirm that each edge is properly represented in the graph at the bottom. This graph is very, very close to the definition for a finite automaton. We just need to add a couple more things to it that we'll get to when we start talking about these simple machines.